So we can calculate how much carbon dioxide is released when a given amount of octane is burned. This chemical reaction provides us the relationships. So this tells us that for 2 molecules of this, we get 16 molecules. Or for 2 moles of this, we get 2 moles of CO2. The coefficients give us the ratio in terms of molecules or moles of each substance. They don't give us mass relationships. They give us relationships between moles. So 2 moles of this gives us 16 moles of that. Every substance, the amount of every substance used and made in the chemical reaction is related to the amounts of all the other substances. Because the law of conservation of mass says that the mass that you start out with is the mass that you end up with. So they are all related. We balance the equations by balancing atoms, but then when we're looking at this numerical relationship, we can also do this in terms of mass, which is more useful. And this whole process of studying these relationships between quantities in chemical reactions is called stoichiometry. And stoichiometry is a big part of what we do in chemistry. So before we go back to talking about CO2, we're going to talk about making pizza. I hope you guys had breakfast. There's another textbook I teach out of, and they talk about making pancakes. So that's even worse at 8 o'clock in the morning. So we can think of a recipe for making any kind of food as being like a chemical equation. You take 1 crust and 5 ounces of tomato sauce and 2 cups of cheese, and you make 1 pizza. Now, it's not a very fancy pizza, but it could be called a pizza. How many pizzas you could make depends on the ingredients that you have on hand, right? And we can express those relationships mathematically. We don't tend to do this in the kitchen, but we could. And what we're going to do here is, using something that we're familiar with, we're going to look at how we relate those numbers so that then we can apply it to something that is strange, like the combustion of octane. So from this equation, we get 1 crust, a ratio, 1 crust to 5 ounces of sauce to 2 cups of cheese to 1 pizza. And so we can take any of these 2 things and have a ratio and relate the quantity of one to the quantity of the other. So we can calculate how many pizzas we could make if we had 10 cups of cheese. You could probably figure that one out in your head just thinking about it, right? 10 cups of cheese, how many pizzas? 5. Yeah. So you did that in your head. Let's see how we would write that down. So this is dimensional analysis again. So, yay, right? 10 cups of cheese.
Are you assuming you have enough for everything else?
Assuming you have enough of everything else. Yes, that is important, and we'll get to that in a later section. So 10 cups of cheese. I need a period after the C. These ratios can be used to make a conversion factor. So I'm going to take my units, and I want to find out how many pizzas. And then I'm starting with cups of cheese, and so I need to divide with cups of cheese to get the units to work out. That's what dimensional analysis does. You do the units first, and the units tell us where to put the numbers. There's no thinking of multiplying, dividing. So pizzas and cups of cheese. Well, the relationship is 2 cups of cheese are needed for every 1 pizza. You get 1 pizza for every 2 cups of cheese. Again, provided you have enough of the other stuff. 1 pizza to 2 cups of cheese. So you do the math there, and you end up with 5 pizzas. Right? You may think, well, that's dumb. Why do you have to write it out like that? Well, you don't for something like this. But if I'm asking you, how many moles of CO2 can you make from 17.34 moles of octane? You can't do that one in your head. Okay? So we need to be able to see how this works out. Any questions? The ratios of the coefficients in a balanced chemical equation also act as conversion factors in the same way. And we can use those to relate any 2 substances. It could be 2 reactants, 2 products, a product and a reactant, any combination we can do in 1 step. So if we burn 22 moles of octane, how many moles of CO2 form? I like to use the balanced chemical equation. to organize information. Here there's not that much information to organize, but let's just practice. So moles of octane, C8H18. So we've got 22.0 moles of the octane. That's the amount of this substance. I'm just going to write it underneath. And then the question is, how many moles of CO2? So under CO2, I'm going to write a question mark, and they're asking for moles. So I'm just pulling the numbers out and organizing them. This is where I'm starting, and this is where I'm going to end up. And a mole-to-mole conversion is just always one step. So I've got 22 moles of octane, and I want to get moles of CO2. So dimensional analysis says then I'm going to divide by moles of octane. So the units work out. Okay. The mole ratio comes from the numbers, the coefficients in the balanced chemical equation. 2 moles of octane would make 16 moles of CO2. So I need 16 moles of CO2, 2 moles of octane. I'm just pulling the numbers out. This number is in front of octane, so I put it in front of moles of octane in the conversion factor. And then I need to do a little math.
Can you reduce it?
You could reduce it. Yeah, you could reduce that to 8 to 1. My experience is that when students do that, you tend to do that reducing in your head, and sometimes you mess up. And it's really not that more difficult to do. Times 16 divided by 2. So you can. I don't necessarily recommend it. So I'm just going to do 22 times 16 divided by 2. I mean, there's plenty of times where we need to think about stuff. But I'm all for finding a process that reduces the amount of thinking we have to do so that we can save our thinking for places that really require the thinking. So my calculator is telling me 176. The unit would be moles of CO2. Because these are both moles, it's important to specify moles of what? Otherwise, you could end up with your 16 and your 2 upside down. We always have to think about sig figs. Our starting number had 3 significant figures. These numbers are exact. The coefficients are exact because they go back to individual molecules. 2 molecules of octane are going to form 16 molecules of CO2, exactly. So these don't affect sig figs, so 3 sig figs there, 3 here. Any questions? Well, we can't measure things in moles. We measure things in grams, right? So we need to expand this idea and start with mass and end up with mass, because we could find out what mass of octane was burned, and we would be more interested in the mass of CO2 that was produced. So this is the general plan, the general path for stoichiometry problems. You start with a mass of one substance. You convert to moles of that substance. You convert to moles of the other substance, and then you convert to mass of that substance. So this conversion factor in the middle is what we just learned how to do. We usually call those mole ratios. So to go from moles of one to moles of the other, you use the mole ratio. That comes from the balanced chemical equation. How do we convert from grams to moles? Molar mass. So that's the molar mass of A. And then over here, we're going from moles to grams. That's, again, the molar mass, but this time the molar mass of B. So we've already covered how to do this first step and the last step. I just taught you the middle, and now we're just going to put these 3 things together. So this path is one that we're going to be using over and over again. And so I call this grams to moles to moles to grams. It's a little shorter than those boxes and all those words and stuff. Grams to moles to moles to grams. That is the basic path for stoichiometry. So if you're not sure what to do, start with grams to moles to moles to grams. Moles are always in the middle. Moles in the middle. Like that show, Malcolm in the Middle. This is moles in the middle. It's never moles to grams to grams to moles. Never. It's always moles in the middle. Sometimes you'll be missing one end or the other, but there's always moles in the middle. Okay? And then we'll see that there are some variations on this. Sometimes we do something other than gram. We could do kilogram here. We could do kilogram there. We'll do some volumes and concentrations and different variations, but this is the basic path. Grams to moles to moles to grams. So let's see how that works. So according to the U.S. Department of Energy, the world burned 3.3 times 10 to the 10 barrels of petroleum in 2013, the equivalent of approximately 3.7 times 10 to the 15 grams of gasoline. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. So here is our balanced chemical equation, same one we've been looking at. So this is saying, so the Department of Energy estimated that this is the amount of petroleum products that were burned in 2013. So petroleum products include all kinds of different things, and so we can't really do a calculation with that. So we're going to make an assumption, an estimation. We're going to say, well, that would be equivalent to this many grams of gasoline. Gasoline is also many different components, but one of the components and a representative one is octane. So we're going to say, well, if it was all octane. Now, this is not going to be a precise calculation, right? This is going to give us a ballpark idea for how much CO2 might have been released. But it's kind of interesting. So this is the number we want to use. It says of gasoline, but we're saying using the combustion of octane. And because this problem is might be a little more interesting, it's also something I wouldn't do to you on a test. But anyway, we're doing it now. 3.7 times 10 to the 15. So we're going to say that the gasoline is octane and that we have that many grams of octane. Calculate the mass of CO2. Okay, so CO2, that's our question mark. And mass, this is going to be grams we're going to want to find. Okay? So I'm using the balanced chemical equation to organize the information. This we'll look at in a minute. So our general path is grams to moles to moles to grams. And if you struggle with this or you're just learning this, write the path out completely before you start. So we're going to start with grams of octane. And we're going to go to moles, grams to moles to moles to grams, moles of octane. So it's grams of what you're given the amount of to moles of what you're given the amount of. In this step, I am changing the unit from grams to moles, but I'm still talking about the same compound. I'm only changing one thing. In the next step, we're going to go to moles of the other thing. So I'm going to go to moles of CO2. Now the unit is staying the same, but the substance is changing. You can only change one thing at a time. You can't just change everything. It's too hard. I don't have to go through oxygen. I can go directly from here to here. It's always just between any two of those substances in the equation. And then for moles of CO2, I'm going to go to grams of CO2. Any questions? Understanding how to do a problem like this is really, really important. So if you're not understanding some of it, please ask. So there's my path. Now I can start the equation. So 3.7 times 10 to the 15 grams of C8H18. 3 arrows, 3 conversion factors. So first I'm going to moles of the octane. And yeah, it gets tedious writing the chemical formula over and over again. Just deal with it. Moles of CO2 and grams of CO2. So I wrote the path, Those units go in the numerator of my terms, and then I put the previous unit in the denominator, grams of C8H18, moles of C8H18, moles of CO2. Okay? This is just dimensional analysis. The units are telling me what to do. Now, once we got the units to work out, we have to find some numbers to put in here. I like to start with the easiest one first, and the easiest one is the mole ratio in the middle. Moles of CO2, moles of octane. That comes from the coefficients here. There's no calculating. You just have to look and copy it down. So there's a 2 in front of C8H18. So I'm going to write a 2 in front of moles of C8H18. Here there's a 16. So I'm going to write a 16. Okay, so that one's done. The first one is a gram to mole conversion. The last one is a gram to mole conversion. I need molar masses. I have to calculate them. So I'm going to calculate them up here at the top. And I really encourage you to just write this out instead of punching it straight into your calculator, because it's easy to forget something and mess it up. So I need 8 times the mass of carbon plus 18 times the mass of hydrogen. 8 times 12.01 plus 18 times 1.008 equals. So calculator says 114.224. That would have 4 sig figs, so the 2 and the 4 can just sit there. That's fine. So this would be grams of octane is equal to 1 mole of octane. That's one way to write the units. Molar mass is the mass in grams of 1 mole of the substance. So that tells me that in my first conversion factor here, where I have moles of octane and grams of octane, 1 mole of octane is 114.224 grams. And then I need the molar mass of CO2, which is 44.01, but we need to demonstrate that. So 12.01 is the mass of a mole of carbon, plus 2 times the mass of oxygen, and it gives us 44.01 grams.
3.3 times 10 to the 10 come into play?
Well, actually, we don't end up using that. So this 3.3 times 10 to the 10th barrels of petroleum, that's a number that's in there, but we don't actually use it in the calculation. So this is kind of a starting point, and then they're saying, well, that much petroleum, we're going to approximate and say, well, that would be equivalent to this amount of gasoline. Because you can't do a calculation like this with petroleum. You need a specific compound. That's a good question. So another way to write the units here is that's grams of CO2 over moles of CO2. This grams per mole and this grams equals 1 mole, that's saying the same thing, they just look a little different. So use whichever one you like. So 1 mole of CO2 weighs 44.01 grams. Then I get my calculator out and I do the math. 3.7 EE15 times 1 divided by 114.224 times 16 divided by 2 times 44.01 equals. Yep. So 1.1404 times 10 to the 16th. And the unit is grams of CO2. How many significant figures should it have? 2. Because this first number only has 2 sig figs. This had 4, that has 4, this is exact. We would like, when we're doing calculations like this, for the starting number to be the limiting significant figure. Otherwise, we should use more digits in our molar masses. So for these calculations, if you have a hard time with significant figures, just use the same number that you started with. So this would be 1.1. So that ultimate answer would be 1.1 times 10 to the 16th. I forgot what I was doing. That's a 0. 10 to the 16th grams of CO2. That's a lot of CO2. So we were talking about volcanoes versus petroleum. Now we're supposed to compare the result. Volcanoes produce 2 times 10 to the 14th grams of CO2 per year. Like, Does anybody have any questions about the calculation? So let's look at that. Here's the mass of petroleum, the mass produced by petroleum, 1.1 times 10 to the 16th. Here's the mass produced by volcanoes. Compare the result. Well, obviously, the mass of CO2 produced by petroleum combustion is larger. How do we compare them? Well, we could see how many times larger it is. So 1.1 times 10 to the 16th grams per year divided by 2 times 10 to the 14th grams per year equals 55. So petroleum combustion produces 55 times more CO2 than the volcanoes. So we can't really be blaming the volcanoes for the increase in CO2. Yes?
And he knows petroleum, just because he put the 1.1 at the top, had to be the switch would be like, we had like the volcano produce and the petroleum combustion produce, been flipped, you would have figured out that it's the petroleum ratio opposed to the volcano.
Yeah, if this number was larger, I'd put this number on top and divide by the smaller one. Because what I'm asking myself was, how many times bigger is the big number than the small number? Yeah. Any questions? So let's do another example. Magnesium hydroxide, which is the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl, according to this reaction. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? So there's a lot of these word problems. When I was in school, we called them story problems, which makes them sound friendlier. The stories aren't really all that entertaining, though. The thing about word problems is that's how you encounter issues in life, right? You have a question, and it ends up being a word problem. You don't, you're like, well, how much stomach acid is this actually going to neutralize? I mean, that's a question you could ask, right? You're not going to be given, oh, what's 3.26 times 5.49, right? That's not a practical thing. So unfortunately, word problems are a part of life, and we need to learn how to understand them. So if you're struggling with that, please ask me for help. So we've got all the words. We've got the balanced chemical equation. Let's use it to organize. So here I've got a number. This problem's nicer. It only gives us one number, so we don't have to worry about which one to use. This is the 1. So this is grams of magnesium hydroxide, so I'm going to write that number and its unit under magnesium hydroxide, 3.26 grams of that. Question, what mass of HCl? So here, question mark, grams. Here we've got 2 reactants that we're looking at. That's fine. Doesn't matter. So grams to moles to moles to grams. That's our path. Grams to moles to moles to grams. You know you're making progress when you wake up in the middle of the night mumbling grams to moles to moles to grams. 3.26 grams of magnesium hydroxide. I need to convert it into moles, convert to the moles of the thing I'm interested in, and then convert back to grams. And you might say, well, isn't there a shorter way to do this? Well, you could figure out a conversion factor directly between mass of this and mass of that, but it would only apply to this particular equation, so it's not very useful. This process can be used on anything, and once you get the hang of it, it's not that bad. So I want to go from grams of magnesium hydroxide to moles of magnesium hydroxide to moles of HCl to grams of HCl. And I write the previous unit in the denominator so they cancel out. And it is really important to write those units. So those cancel, and then grams. We've got moles in the middle here. So moles in the middle, that's the easy one. We look at this, and in front of magnesium hydroxide, there's no number. That's an understood 1. So I'm going to write 1 in front of moles of magnesium hydroxide. There's 2 moles of HCl. Because 1 mole of this will neutralize 2 moles of that. The first one and the last one are molar masses. So we're going to be calculating a lot of molar masses, and so we need that to be kind of old hat. So HCl, that's 1 hydrogen, 1 mole of hydrogen, plus 1 mole of chlorine. So 36.458 grams per mole. So that's the one on the end. I did that first because that one's easier. 36.458 per 1. And magnesium hydroxide. Okay, that's going to be a little more of a calculation. Thank you for giving me that, but I have to do it anyway. So you can just correct me when I screw up. 24.51. 31. Dang. 24.31. Okay. 1 magnesium, 2 oxygens, and 2 hydrogens. $58.326. Awesome. The 2 of us got it right. Of course, I can't write it. It's hard to write one thing while you're saying something else. But sometimes I even can't write it when I'm saying the thing I'm writing. And then there's the train. So that's the molar mass of magnesium hydroxide. So moles of magnesium hydroxide are on top. That's where the 1 goes, and the number goes with the grams. Okay. 3.26 divided by 58.326 times 2 times 36.458 equals 4.075. Need 1 more. 4. So this number has 3 significant figures. All of these have 4 or more, so this would be 3 significant figures, and I'm going to round that to 4.08 grams of HCl. So 1 dose of milk of magnesia would neutralize 4.08 grams of HCl in your stomach. You've got hydrochloric acid in your stomach. Did you know that? And it's a good thing, because if you didn't have the acid in your stomach, you wouldn't be able to digest your food, and you would die. So, yeah. Any questions? Another one. A component of acid rain is nitric acid, which forms when NO2, which is also a pollutant, reacts with oxygen and water according to this simplified equation. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming there's adequate oxygen and water, which, in the atmosphere there's probably plenty of that, what mass of nitric acid in kilograms can form from this amount of NO2 pollutant? Okay, so this one has a whole bunch of words in it, but it still only has the one number. So 16 kilograms of NO2. So let's write that in here. Find NO2 and write 16 kilograms underneath. That's the information I'm given. The question is, what mass of HNO3 in kilograms? So I find that in the chemical formula, question mark here, and they want kilograms, so I write that unit down. So our normal path is grams to moles to grams. But here I'm starting with kilograms and I'm ending with kilograms. What do I do? We can add extra steps, okay? And so there's more than one way to do this problem correctly, and which way you do depends on how your brain works. So you do the one that makes the most sense to you. So one method is, well, I'm going to start with kilograms. I'm going to convert that into grams. Then I can do my grams to moles to grams. Then I need kilograms at the end, so I'm going to convert it back to kilograms. That is an entirely fine way to do it. But let's think about what's happening here. What's the conversion factor, grams to kilograms? 10 to the third grams per kilogram. So that's what I'm going to use over there. And over here, I'm going to have kilograms on top and grams on the bottom. 1 kilogram is 10 to the third grams. I'm going to multiply by this factor at the beginning and this factor at the end. They're going to cancel each other out, aren't they? So we can actually do a little bit of a shortcut. I'm going to show you the shortcut. If you don't like the shortcut, you are very welcome to do this. There's nothing wrong with it. So I'm going to start with kilograms. So 16, I'm going to write kilo in red. And I have a reason for doing that. So 16 kilograms. I'm going to ignore that red kilo. Kilo just means 1,000, so K is standing in for a number there. I'm going to ignore the kilo and just deal with the rest of it. Okay, I'm going to pretend I've got grams, just for now. So from grams, I'm going to go to moles. Oops, I forgot to write kilograms of what? That's kind of important. Kilograms of NO2. So then I'm going to go to moles of NO2. And then I'm going to go to moles of where the question mark is, HNO3. And then I want to find, well, I'm just doing grams to moles to grams right now. I'm ignoring the kilo business. So I'm going to have moles of HNO3 down here. Psst, what? Okay. I just left out the unit. That's not cool. There we go. And moles of NO2 down here. And grams of NO2 down here. So what I'm doing is I'm just mentally setting that kilo aside. And I'm going to do grams to moles to grams. So I need to fill in my numbers. Moles in the middle, that's the easiest one. Here it's 4 moles of NO2 to 4 moles of nitric acid. So 4 moles of nitric acid, 4 moles of NO2. Could you simplify that? Sure you could. Then we need molar masses for our two substances. So NO2 seems easier, so I'm going to do that one first. So 14.01 plus 2 times 16. This one is 46.01. So that's the molar mass for NO2. So molar mass for NO2 is first. 1 mole is 46.01 grams. Okay? Then I have to calculate the molar mass for nitric acid, so the HNO3. So that's going to be 1.008 plus 14.01, and 3 times oxygen. $63.018. Grams over moles. That's for the HNO3. So in my last term, 63.018 grams of nitric acid is equal to 1 mole of nitric acid. So let's look what's happening here. Here I have kilograms of NO2 and grams of NO2 down there. So if I leave the kilo out of this, those cancel out, right? The unit that's left uncanceled is grams of nitric acid, and I've still got kilo multiplied in here. So the unit I end up with here is kilograms. Oops. Issues. Kilograms of HNO3. I just set the kilo aside. I didn't cancel it out, and so it's just going to sit here. The reason that works is because if I did the conversions just cancel each other out. You can do that. I don't like to. So I'm going to do this math. 16 divided by 46.01 times 4 divided by 4 times 63.018 equals, based on my starting number of 16 kilograms, I should have 2 significant figures. That's a whole number, but kilogram is a measurement. You can't count kilograms, so it is 2 sig figs. It's not exact. So 2 sig figs would be 21, and then write down 2 extras, 91, and then we'll round that, and this is 22 kilograms of nitric acid. That's about 50 pounds of nitric acid. That's a lot. Any questions? Yeah?
How did you get from grams to kilograms?
How did I get from grams to kilograms? What I did is I didn't cancel out the kilo here. I canceled out grams of NO2 with grams of NO2. And so after I cancel out everything else, I have grams of HNO3 times the kilo.
Kilo is 1,000.
Kilo means 1,000. So there's several different ways you could do this. You can do the actual conversion at the beginning and the end. Another thing that works out pretty well is related to an exercise we did on one of the worksheets. Replace the prefix with its multiple. So 16 kilograms is 16 times 10 to the third grams. And that you can just write that down as you're starting, and then you'll end up converting back to kilograms at the end, but at least you don't feel like you're doing and undoing the same thing. So this is the sort of variation on this overall process that you're going to see, okay? So here I've shown you how to do the kilograms to kilograms, but there could be on a test. Start with grams and end up with kilograms. Or giving you the volume of a cube and the density, so you have to calculate the mass, and then getting a mass at the end. Or giving you pounds and asking you for ounces and making you do English metric conversions in between. I mean, there's all kinds of things that could happen. And so you need to understand how to convert units, how to do stoichiometry, and how to put those two ideas together. That's very important.